Right, this is Edx M3 Jun 2011, question 5. It's on elastic strings and elastic potential energy and work done. Here's the question. As usual, you probably need to pause the video and read the question carefully and continue when you're ready. So for the first part of the question, we're told we've got a particle of mass m on a rough table, coefficient of friction mu. I've got the first part of the question ready here, and I've drawn a diagram, but I haven't labelled it with any forces yet. So this is the particle of mass m over here. This is mg. Then let's just that's the weight of the particle mg. That's the reaction. Here's the tension in the string, and here's the frictional force. Now we want to show that mu is greater or equal to half. Reading the question carefully, the particle is currently at rest on the table. So the critical value for the coefficient of friction will be when it's only just rough enough for this to be there in limiting equilibrium. So what I'll do is I'll say assume the friction is limiting, and that means it's equal to mu r. So it's at its maximum value, and the particle is only just managing to stay there. Okay. So let's go on with that now then. First of all, it's clear that r equals mg. The only forces vertically, they balance. And the second thing we can say, reading the question, the extension x equals L over 6. So the tension in the string is lambda x over L. That's the expression for it. In this case then it becomes 3 mg over L times L over 6. So the tension is mg over 2. Okay, I think you can see where we're going with this then. So if the tension is equal to mu r, then mg over 2 equals mu mg, which gives us mu would have to be a half. So mu equals a half would be required for this to be in limiting equilibrium on the point of slipping. So for it to be safe, effectively, mu has to be greater than or equal to half for equilibrium to be possible. And 4 marks for that. While we're here, the 4 marks, the allocation of the 4 marks were just 2 method marks and 2 accuracy marks. Well, in fact, there was one mark, a B mark for seeing this. T1 equals lambda x over L equals mg over 2. So there's 1 mark for that. Then there was a method mark for basically either saying that either evaluating the friction equal to mg over 2, and then saying the friction is less than or equal to mu r, or doing what I've done here and putting friction equal to mu r and then evaluating it. So let's just see, there was 4 marks, B1, oh no, there's 2 method marks. There was accuracy method, oh of course, right, method mark for that. So there's a method mark for using Hooke's law, and a method mark for saying that the friction is limiting, and then 2 other marks, and that's the 4 marks. Right, on we go. Now here's the rest of the question. So it's moved further along, and now this is 0.5 L, the extension here. Now then, let's just label that. There's L, there's 0.5 L. L is the natural length. And it's released from rest. Mu equals a half here. So the frictional force, if it's released and starts sliding, equals mu r equals 1/2 mg. There's r, there's mg, and there's friction. Right, find the speed of p at the instant when the string becomes slack. Let's use energy for that then. So for part B, the elastic potential energy goes to kinetic energy, and that's all that would happen if the table was smooth, but there's some that will have disappeared because it will have been used against as work done against friction. Okay, so that's what we've got to do for this bit. I'm putting in the values here then. The elastic potential energy at B is lambda x squared over 2L, which works out to be 3 mg. Check this yourself, pause the video and just check that you get that. 3 mgl over 8. That goes to half mv squared plus a half mg times the distance it's moved, which is 0.5L for when the string goes slack. Okay, we're there now. We can just cancel out the m's and tidy this up. We get 4v squared equals gl. So v squared equals gl over 4. Therefore v is root gl over 2. That's part C. Part B, beg your pardon. Part C, the total distance moved by P before it comes to rest again. Well, we've just found the speed here when it went slack. That's where the speed was, v. Right, the total distance moved by P before it comes to rest again for part C is nice and easy. It loses the kinetic energy, K lost, and all of that is used up as work done against friction. Work done against friction. I'll call that FR for friction. So we've got a half m v squared, which is a half m gl over 4, is equal to work done against friction. Half mg is the frictional force times the distance. Let's call the distance d. So take a moment to check it. D works out to be L over 4. And the total distance then is 3L over 4. Right, well that was a simple last part, and there was 3 marks for that. For the 8 marks for parts B and part C then, for part B for 5 marks, there was 1 method mark for using energy. There was a B1 for seeing the elastic potential energy, correct? That's 2. There was a B1 for seeing the other terms in the energy equation. And there was 2 accuracy marks for dealing with that and finding the correct value of V. 1, 2, 3, 4, 5, right. 3 marks for this last bit, a method mark for the energy equation again, and 2 accuracy marks for sorting that out and finding the distance. Yeah, that's right. So, thanks for listening. That's June 2011, question 5.